Welcome back to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. Let's try to recall what we were studying in the last session. We saw how through a series of logical steps, we saw that only the pass gate transistor and pull down transistor were the active component during a read cycle. That is because all other transistors were off. As a result, there was a read current flowing through the pass gate transistor and pull down transistor. And we also saw how through appropriate cell maintaining an appropriate cell ratio through transistor sizing, we can ensure that the delta V dash which develops on the internal storage node 0 is kept to a minimum, and therefore we facilitate a non-destructive read. But let's try to recognize that all the analysis we did here the last time was more like static analysis. We were assuming through this voltage divider circuit that all these are DC signals and these things are not changing with time, but actually that is not the case. Read cycles happen within a very short duration, and it is worthwhile to look at what the dynamic analysis of the read operation is, and this can be done by looking at timing diagrams. So what essentially are these timing diagrams? So timing diagrams are diagrams where we on x-axis place the time axis, and on y-axis we track what is happening to the different voltages at different nodes in the SRAM cell. Okay, so before that, let us try to recall. Here we had storage node N1 was 0, storage node N2 was 1, and there was a read current flowing from PG1 to PD1, which was resulting in the bit line being discharged from VDD to VDD minus delta, and that is what was getting detected by your sense amplifier as a 0 when you were comparing the value of bit line versus bit line bar. So this is what was happening. So how are all these processes happening one after the other is what we will see in the timing analysis. So in the topmost panel of your timing analysis, today we will track two important signals, which is bit line and bit line bar. Okay. In the second panel, we will track what is happening to the word line from 0 to VDD, right? And in the third panel, we will closely look at what is happening to the voltages at the internal storage nodes VN2 and VN1. Okay, so this is what we will be doing, and we will see one after the other when the word line is asserted, what are the changes that happen to all these different voltages. So right at the beginning, the bit line and bit line bar are first pre-charged to VDD. Please recall, both bit line and bit line bar are pre-charged to VDD. This is what I have indicated over here, and I'm pointing through my laser pointer that bit line and bit line bar have been pre-charged to VDD, and only after that the word line is asserted. Okay, the initial conditions, voltage at VN1 is at 0 and VN2 is at VDD. What do you expect next to happen? The moment you turn on word line, you would expect that a read current will start flowing from your PG1 into PD1, resulting in a discharge of your bit line. And that is what is represented over here. There will be a discharge in the bit line. You see, there is this bit line, and that is effectively getting discharged. Discharge means the value is going to reduce from VDD to some minus delta. Okay. What is going to happen along with that? Because a read current is flowing, we also saw that the value at this storage node 1 cannot remain at a fixed value of 0. So there will be an increase in the voltage of storage node 1, which we will say is delta V. And please recall from our previous lecture, by appropriate transistor sizing, we ensure that this delta V is very small. As you can see in the axis, in the y-axis from 0 to VDD, the delta V is quite tiny. Okay, this delta V is kept tiny through cell ratio and kept much smaller than the noise margin of your SRAM cell. But this is where the first deviation we see from our static analysis. During your static analysis, we saw that storage node 2 we were not bothered about. We were not seeing what is happening at storage node 2, and we assumed that nothing is really changing at storage node 2. Right? The voltage at storage node 2 is fixed at 1. But in the timing analysis, we clearly see while there is an increase in the value in storage node 1 from 0 to plus delta V, there is also a reduction in the value from storage node V2, right? Vn2 is, you see, is going down from VDD to 0, is reducing from VDD to minus some delta V dash. Okay. So why is this happening? Please take a moment to pause the video, think very carefully. Something that was not accounted for in the DC static analysis, we see in the timing analysis that Vn2 is also changing. Why do you think this is happening? So if you have been following the course carefully, when we were doing our analysis, bouncing off the butterfly loops, at that time we saw that a small disturbance in storage node 1 or N1, when it was bouncing off the blue inverter, the inverter 1, we saw that there was also a change in the voltage at the storage node 2. That was reducing from VDD to minus V dash, right? So any changes in the cross-coupled inverter, any small change in the input will also lead to an change in the output. The speciality of the cross-coupled inverter is, if these disturbances are tiny, you will be able to regeneratively pull back the system to its original state, right? And this is what we see in the next graph. We see that these voltage nodes N1 and N2 are kept under check or kept under control, so that they do not flip, because the delta V by the virtue of cell ratio was kept below the noise margin. However, by this time, what has happened is the bit line, the voltage drop across bit line is significant for the sense amplifier to make a decision and say that this is quite a significant difference between bit line and bit line bar, and as a result, the sense amplifier asserts its signal saying, I am done with my job or I am finished. The moment the sense amplifier asserts the sense amplifier enabled signal, the word line is immediately deasserted. Why is the word line deasserted? Because you want to indicate that your read operation is completed, and therefore you want to decouple pass gate 1 and pass gate 2 from the from bit line and storage node 1. Okay, so the moment the word line is deasserted, the bit line automatically, which is pre-charged from the external circuitry, return back to its original position, and also you see that Vn1 and Vn2 also stabilize. Vn1 stabilizes and parallelly Vn2 also stabilizes, and a good question to ask at this point would be, why does Vn1 and Vn2 stabilize? And I hope you can answer from your previous understandings that this is due to two factors. First is, you are not allowing delta V to go beyond the noise margin. This was facilitated by intelligent design through transistor sizing in the cell ratio. Remember what the cell ratio was? It was the W by L ratio of the pull down transistor versus the pass gate transistor. The ratio between the W by L ratio of pull down transistor to pass gate transistor should always be greater than 1, because the drive strength of pull down transistor should be always greater than the pass gate transistor to make sure that the storage node N1 is closer to VDD, right? That's why pull down transistor should be stronger. Not only this, the other important aspect is all of this would not have mattered until there was a finite noise margin, which was a result of the positive regenerative feedback of these cross-coupled inverters. And this is what concludes our timing analysis of the SRAM cell. Here I would like to ask you two questions, open questions, which I would like for you to think about, and maybe we will discuss in the next class. The first question is, we saw through our dynamic analysis that voltage node N2 is also getting disturbed a bit. If voltage node N2 becomes 1 minus delta V, does our initial consideration or initial assumption that pass gate 2 is still off still valid? That is the first question that I would like to ask you. I will repeat. The first question is, during our static analysis, we just assume the voltage at N2 does not change at all. Now we are seeing that is not really the case. Albeit small, but there is a small drop in Vn2 also. Now if Vn2 drops by 1 VDD minus delta V dash, does the pass gate, does it change our analysis? Does the pass gate to transistor turn on? That is the first question. The second question, and a more open question, is what was the need to have bitline and bitline bar pre-charged only to VDD? Why don't we keep it at 0? If both with the same analysis that we did in the previous session, you can show that read operation is possible even when bitline and bitline bar are charged or grounded to 0. It is not necessary to make them VDD. So why is this preference to have it only in VDD? Please think about this, and we will discuss in the next session. Thank you.